it? Okay, very good. So should I start on time? Okay. So good afternoon, everybody. We are starting now our quant. Okay, just a minute. Let me just. Sorry, I was just. So again, good afternoon, everybody. Welcome again to our QuantHab seminar. Today we have a seminar by Fred. I hope I will pronounce his name correctly. Jendrzejewski. It's okay.
Fred was fine.
For me as a particle physicist, this is a very interesting seminar because for once we are receiving an experimental physicist, but who is not working directly on high energy experiments, but on quantum simulations for high energy physics. Quantum simulations, in this case, it's really important in this context. And Fred will be talking about engineering local U1 symmetries in artificial systems. Of course, this is quite an important subject for high energy physics, because if anything else, we would like to know how to implement electromagnetism in particle physics. So without further ado, Fred, thank you very much for accepting our invitation, and I leave to you the floor. Thank you again.
Thank you very much for the invitation, actually. I will try to start it. Can everyone see this now with the presentation? It's working out?
Yes.
Very well. So as I said, thanks a lot for the presentation, for the invitation. It's quite special for me to talk here. It has become a topic which is very dear to my heart and to our group, to try to study high energy physics with cold atoms. And as you can see, by no means am I alone in this topic. I'm actually only a small part of this. A lot of the hard work, or the hard work, is done by the students in the lab and implementing this. And on the second side of things is we are atomic physicists in the lab, and naturally the high energy physics, we need some theorists to explain us how to involve this and what are the important questions there. And so we are very grateful for these collaborations too. So what are we trying to do? In the experiment, we have a lot of lasers and beams there, and we produce very cold atoms, which are almost at zero temperature, and then we have very good control over them, and we can perform nice quantum systems and quantum simulation. And we would like to know, can we use these systems to study high energy physics? And I would like now to present you first, how does it look in the lab? What do we have? And then again, our naive point of view of what are we trying to study here? What is this picture? Because this is, as you know, what we know about particle physics quite often when we start out in this topic. In the lab, it typically looks like this. So this is built by us. These are machines which we have an empty lab, and then we build them up here. We need first lasers on this desk here to cool down the atoms. This is the first ingredient. Then we need a lot of electronics and control systems to control the machine and have a quantum simulator running. And on this side here, we have the optical table, where we have a vacuum system where we are able to isolate the atoms from the environment such that we can cool them down there. So we don't need to have any kind of fridge or liquid helium or anything like this. It's just done by vacuum, which isolates us from the environment. And this allows us to have this very well-controlled quantum system. And now you might wonder, where are the cold atoms in all of this? And they actually are here. If you zoom in into this vacuum chamber, this little yellow dot here, these are the atoms which are roughly at 1 millikelvin fluorescing here. These are sodium atoms which we cool down. And our first ingredient then is with yellow light, we cool down sodium atoms, which we will later use for the implementation of a Metafield in the quantum simulator, as you can see here. But we also can change the color and cool down a second atomic species, which are our lithium atoms. And you will later see that we use these two atomic species one as the gauge field and one as the Metafield for our quantum simulator. Okay. And now we have these tools, and why are we doing this? Well, the possibilities that we have in the system is we have a very clean system here. We have very high control over the confinement of our atoms. We can basically decide if we want to implement a 1D, 2D, or 3D system, or actually a system where the motional degrees of freedom don't play a role at all, and we can only look into other degrees of freedom. We can very well control the temperature. We might be in a regime of hot temperatures where quantum effects are not so important, or very low temperatures where we can really see the quantum effects and the bosonic or fermionic statistics of the system. The third ingredient is we can work with the spin, very much like with the qubit devices. The spin is a very precisely controlled degree of freedom in our system. And finally, we have well-controlled interactions. So if two atoms sit at the same position, we have this contact interaction, which actually allows us to study complicated systems. And in general, we then have this Hamiltonian, which describes any experiments that we have in our system. So the first part of the Hamiltonian here, this is the kinetic energy, the potential energy, the magnetic field. And then here, these red things are the contact, is the strength of the contact interaction, which is basically given by nature, or which we control. And then we, as experimentalists, change all these parameters, the interaction, the magnetic field, and the potential, for example, to study interesting systems. So we use these toolbox to emulate interesting problems that we would like to study with the help of theorists. But like whenever we do our experiments, we're forcing the Hamiltonian to look like the system we want to study. And today we want to really study how can we force this Hamiltonian to implement problems which are known from high energy physics. So what is high energy physics from the atomic physics point of view? The first problem that we typically have already is that all our problems in called atomic physics are formulated with Hamiltonians. We never work with Lagrangians or things like that. And then whenever we open a high energy physics books, a lot of the physics is described in Lagrangians. And they have two ingredients. You have this blue part, which describes the particle dynamics or the Dirac equations. And you have the second ingredient, which describes the gauge field or the electromagnetic field. And even if you're not just using QED, but you look at the Lagrangian, which is the much harder one, the QCD Lagrangian, again, it has a very similar structure. You have the matter part and you have the gauge field. And somehow they have to follow certain rules, right? How did these Lagrangians come along? You do these collider experiments, and while they are extremely complicated, they also follow a very simple set of rules, namely local conservation laws. You create a certain charge and a certain particle, and it can only decay under the conservation of charges. And what does this mean? That these gauge fields and the particles, they're coupled through these local symmetries. And this is then what we learned we have to implement here. We have to couple the particle to the gauge field such that we have these local conservation laws. So again, I'm trying to translate the high energy physics world into the very simple terms that we try to implement in the lab. And what we learned is that from high energy physics, we have these conserved local charges. And already from classical physics and the Noether theorem, we know that from conserved local charges, there comes a conserved local symmetry. And this is actually the Gauss law, which implements this. So how do we visualize this? Again, let's assume that we have an atom, which is here these blue guys, hopping through a lattice and emulating the Metafield. Now I can directly tell you that this fulfilled point here signals that there's an atom or a metaparticle present. And now, what is the electric field? Well, from Gauss law, we know that the electric field has to pinpoint directly to the direction of where this particle sits. And now, as the particle hops, the Gauss law tells us that the electric field connecting the lattice sides has to flip too. So we have this very strong correspondence that if in one dimension a matter a particle hops, the electric field also has to change. And we have to implement this in the lab. This is basically the very much needed cooking recipe that we have to fulfill the Gauss law there and look into this. So besides having something interesting to work on and implementing these very controlled systems, is there actually something where we might help the high energy physicists to solve open problems? And I really like the picture of the Schrdinger pair production, because I think it's fairly straightforward to understand as an experimentalist. You basically want to take two metal plates and a capacitor, and then you try to charge it up as much as possible. And the question is, when do you break it? So it's always fun to break things as an experimentalist, and you want to know when do you break a capacitor by charging it too much. And what you directly learn is that if you put this these two metal plates into vacuum, into classical vacuum, you should be able to charge the system infinitely high. However, in quantum mechanics, this vacuum is not entirely empty. In this vacuum, you can have particle hole excitations or particle antiparticle excitations, which are present there. And at some point, the electric field is so strong that it's actually an advantage to create an antiparticle-particle pair. It costs you the mass of these particles, but it allows you to discharge the capacitor and lower the electric field energy. Now, the question is, at which stage can this be achieved? And the electric fields that you would need for this are actually enormously high. They're at 10 to the 18 volts per meter. And just to give you a few scales, lightnings are at 10 to the 5 volts per meter. The diamond is 10 to the 9. This is the highest we can do naturally in static pressures here. So we have another 9 orders of magnitude to go to see this in the real world in this version. So the question is then very nicely posed for us: can we construct a quantum simulator for such an effect? It's not just can we do high energy physics in absolute, but can we build a little quantum simulator for this system and study it in the experiment? Okay? So this is the goal, basically, as in the first step. And we were not the first to start on this. The first really pioneering experiment in this direction were performed with ions in the group of Rainer Blatt and Peter Solar, where they took 4 ions, which they controlled extremely well, and they were able to implement a quantum simulator for Schrdinger pair production in 2016. Now, I think everyone agrees that 4 ions is a fairly small system, and you would like to scale this up to a bigger size. And then 3 years later, they were actually able to use a different kind of algorithm and a larger system with, I think these are 19 ions, which they used here to study these physics. The question is, can we go even higher with cold atoms? And what can we do with our system here? So we will have a very different approach. We will directly try to implement the high energy system that is given to us. So what are the ingredients that we would like to use? The first thing here is we have our sodium atoms. And these sodium atoms we would like to use as the gauge field. Already here you will see that this is very different to the quantum simulation platform of the ions. We're talking here not about a few ions in the order of 10. We are talking here about a few 100,000 atoms. Yeah. Further, the timescales are typically quite different. We are much slower on the timescales than the ions. So the ions, they have typically relatively small systems, but extremely well controlled. And for the atoms, you give up some control, but you're able to have much larger atom numbers and also larger systems on the scalability side, as a rule of thumb there. So this is the sodium atoms, which we want to use as the gauge fields. And then the second ingredient is we have our bosonic lithium atoms. And they are what we would like to use for the Metafield. Here we have much less lithium atoms, but it's still 60,000 atoms. Okay, so it's still a lot compared to other systems. Now we know what the two atomic species are that we would like to use. We also know what is the system that we would like to look at. Schrdinger pair production, what's the Hamiltonian that we have to implement in our experiment. So this is always where the interaction with the high energy physicists and the theorists is extremely important. They basically tell us which Hamiltonian should we quantum simulate in the lab, and then we go into the lab and attempt to implement it as properly as possible. The first ingredient is we have to implement somehow the gauge field, the electric field, and the energy cost of having stronger and stronger electric fields. And this will be done with the sodium atoms. And here we use the formulation of Schrdinger bosons. And we will encode the electric field in the Z component of a long collective spin. How is this implemented in the lab, such a long collective spin? We have condensed the sodium atoms all into one motional state, which we can from there on ignore. So we have something here like 7 atoms, which can be either in the state down or up. And clicking through them, this implements a spin of length 7. And we can then look, does this Hamiltonian get implemented in our system? And yes, it does naturally get implemented through the interaction with between the sodium atoms. So the fact alone that the sodium atoms interact can be expressed in this term, which is naturally implemented in the lab. In cold atoms, we typically call this one the one-axis twisting Hamiltonian. Now, the second thing that we need is the Metafield. And here, for the Metafield, it needs to describe the fact that it costs energy to take particles out of the vacuum. And the simplest way to express this is through such a term. Again, we take our lithium atoms, we condense them down into one motional state such that we can only focus onto spin states. And then we label one of the spin states V and the other one P. And the idea of particle production is then that a particle goes from the spin down to the spin up state. And given that our atoms are in a magnetic field, this will cost some energy to do this switch. And this energy shift is exactly the term that we would like to implement in the experiment. So we have the gauge the Hamiltonian that describes the gauge field that is naturally implemented, the Hamiltonian that describes the Metafield, and now we need to connect them properly such that we have a local gauge invariance. And now the great thing about U1 is that even this U1 symmetry is naturally implemented for us. So what I said at the beginning is we need to make sure that if the particle moves, the electric field changes too. This is the Gauss law, basically, that tells us this, right? How do we do this? In this Hamiltonian, if I have a particle that goes into the vacuum, I change the electric field, and the other way around. How does it get translated into the atomic world? Well, we work with spins. And if a particle goes from the V state to the P state, this means that the spin of the particle of the lithium atoms has to change here. It has to do this up motion. And for the electric field, it directly means that it needs to flip down. So we have so-called spin changing collisions, which directly implement this Hamiltonian that we want from high energy physics. Yeah. So the game is basically, we look at the Hamiltonian coming from high energy physics, and then we attempt to isolate the system so well that only the 3 processes which are important to be quantum simulated are leading in our system here. And this is exactly what we set up. We work at a certain magnetic field, we cool down the atoms, we prepare them in the proper state. And we think now that we implement this Hamiltonian. And now as an experimentalist, we have to prove you that we actually can do this and not just say that it's possible, right? This is our experimental work. So now I would like to walk you through our experimental protocols that we did to make sure that our situation works and it's not just ideas. Somehow, is it possible that the mouse is gone, the pointer? Can you see the pointer, or is it gone?
Right now it doesn't show.
Okay.
Yeah, now it's okay.
Now it's back, and let me do this again. So now the pointer should be back, right? Yes. So all our experiments are following this basic protocol. We prepare the lithium at all the particles in this V state. We prepare the electric field to be fully polarized, the spin at the bottom. Then we do some manipulation and evolution, and in the end, we read out what is the spin of the electric field and in which state, in the V state or in the P state, do the metaparticles sit. This is always the same sequence that we will go through. And now if we want to look at what does the electric field do to our metaparticles, we first have to verify that we can change the electric field properly without disturbing the metafield. How do we do this? Is, as I said, we initialize the system and then do a rotation around the x-axis of our collective spin and read out that we can nicely tune this. So, atomic physics, we call this a Rabi oscillation. It's a very standard thing to do. And we can nicely see that we can indeed tune the spin from fully negatively polarized to fully up-polarized. And this now gives us control over the electric field. And we see also that changing the electric field at the beginning does not change anything on the metafield. So we have good control over the electric field part. Now we would like to see how does this electric field have an influence on the dynamics of the metafield. What we will do for that is we will select one very specific position of the electric field that we apply, and then we see how does the metafield evolve over time. We apply an electric field, we let the metafield evolve over time, and we read out where do the atoms sit. Yeah. And this is then what we get out in the lab. Here the time scale is in the order of 30 milliseconds, and we can see that we always keep a lot of particles in this vacuum state, but that we have some particles oscillating out into the P state, they go back and so on. So these are the raw images that we have. And now to quantitatively understand better what we are doing, we just integrate up the number of atoms in these pictures that we get from the camera, and then we get out such a profile, right? So this is now here, we start at no atoms in the P state whatsoever, they oscillate here. And now we would like to understand, this already looks like clear coherent dynamics. We have these oscillations. Are these dynamics now well described by the Hamiltonian that we wanted to implement? So what we do is we take this set of data and all the other data that I will show you today and describe them by solving in the mean field limit the motion for one set of chi, delta, and lambda. So in the experiment, we implement them effectively. We choose this chi, delta, and lambda, and then we test all the data. And what we can see is nicely describing our experimental results here. And what does it describe? I apply an electric field, and due to the electric field, I create some particles. Now I would like to understand, is this only for this set of electric fields? But how does it change for other electric fields? What is the influence here? What we can see is by applying a stronger electric field, the dynamics get slightly faster and stronger. Again, plugging in these initial conditions into the equations of motion, we can nicely see good agreement with the predictions of the theory here. Now we can clearly see, first, we have verified that we can see dynamics. We have second verified that these dynamics for two sets of data are well described by the equations of motion, but can we push this dependence of the metafield to the electric field further and understand this really systematically over the full range? So what we do is we will take a slice of these time evolutions after 30 milliseconds for different electric fields, okay? So we change the electric field, let the atoms evolve for 30 milliseconds, take a picture and see how many atoms have gone into this P state up there. And this is now what you see here. On this side, when the spin is fully polarized and there's the fully applied electric field, you can see that there are no dynamics whatsoever in the metafield. Then in this middle region, these two bars are the two data sets that I showed you. You can see that there's very clearly a behavior of I produce particles into the p states, and then I get once again off resonant and the particle production falls down. We once again verified in detail that this is well described by our experimental, by the theory, giving us a lot of confidence that we really understand that for this Hamiltonian, we can change the electric field and understand what's going on. And in the last step, we would also like to make sure that we can tune the mass, the effective mass or the energy cost of creating particles, and how does this influence the dynamics that we're observing. And what we can see then is, this is the data set that I have shown you. And this parameter delta, this energy cost, we can directly control this by changing the applied magnetic field. So what we did is we took the data that we took here and re-perform exactly the same experiment, just at a slightly different set of magnetic fields. And what we can see is, yes, for a different energy cost of producing the particles, the resonance, the production of particles is actually also moving exactly as expected. And it's also moving in the expected direction. It costs more energy. You need to apply stronger magnetic fields for stronger particle costs here. So here again, we always compare this to the theory, and we have always this very nice agreement. So taking all of this together, what this told us is, it seems that we have a very good control over this building block on the single atom, and we should now start to move on and actually try to implement this in a larger system and in the lattice system. Not yet in 2 dimensions or 3 dimensions, but let's move from this building block to 1 dimensions. And if I'm in 1 dimensions, what I want to have is I have a matter field on different sides, and they are connected through this gauge field. And then I have the dynamics that I described. And to implement such kind of a Hamiltonian, what we can do is we take the building block that I presented to you previously and put it into an optical lattice. The optical lattices we just get by interfering 2 beams at the same frequency, and then the periodic pattern, the atoms sit in the intensity minimum. And this is here such a lattice that you can see where we perform the experiments then. And on each matter side, we implement this building block, and now we need to connect it properly such that we get the right positions. And this connection is then done through Raman lasers, which couple hopping to a spin flip. We're working on this. We have not finished it yet. These experiments are hard, but we're making good progress. Okay. So this is this side. I have presented you our experimental results on the first building block. We have started to study the interesting physics that could be investigated in 1 dimensions with such a system. This was theory work in collaboration with the group of Jürgen Berges and Thorsten Zache, where we found that you can actually observe in very similar systems if you replace the lithium 6 with lithium 7 with lithium 6, that you might be able to see dynamic phase transitions here in such a system. And we have now started also, given that we have a fairly clear plan on how to go to 1 dimension, how would we go to 2 dimensions? There's now a recent work on the archive by Robert Ott and Jürgen Berges. And we have also started to wonder, could we implement maybe non-abelian gauge fields? These non-abelian gauge fields, they're so unnatural to atomic physics that we might have to play new tricks there to go there. And we have started to look through new tricks with dynamical decoupling, basically, for these kind of systems to get there. So this brings me to the end of the very first part. And if there are questions, it might be a good moment for these questions, as I will then slightly switch topic, and it's a natural breaking point here if needed or wanted.
I actually have a question. You
Yes.
mentioned that you have a phase transition here. I mean, how do you see that? in practice?
So this is actually a phase transition in the dynamics. So you prepare your system, and then you have to measure this rate function over time. So you prepare the system, you quench the tunneling element, which is this, I think it's the lambda parameter. And what this tunneling element, this quench in the tunneling element tells you is that you're going from one topological phase into another topological phase. And as you then look at this quantity here, what you can see are these very sharp cusps in the dynamics. So it's a dynamic effect. And these very sharp cusps are actually associated with this topological index that you can measure through the appropriate correlation functions. Don't name me down right now on the proper definitions. But what you can see is then whenever you have the cusp, this topological index is switching very distinctively. Okay, so yes, so this is the transition that I mean. It transitions from one topological index to the next one over time. Does this answer the question?
Yes, thank you.
I also have another quick question. So you have shown the very nice agreement between the experimental results and your numerical simulations, which anyhow had a small, discrepancies. And you were mentioning that your simulation were made in mean field approximation.
Yes.
So my question is if these discrepancies arises from this approximation or maybe some other effects. So do you have?
Yes. So we, I don't have the appropriate data because it's heavily in work, but we are actually working very actively into this. What happens if we go in the theory beyond mean field, and on the mean field itself, we can say I think two things by now. That we see that these oscillations are damped, and the damping is to a non-negligible part due to quantum fluctuations. We had not this, like this was something that we had to put in by hand in the mean field description, of course. So the quantum fluctuations are, partially responsible for the damping. The second thing is, if you look at these data here, the error bars are quite small on the mean because we had to take 30 to 40 data points per shot here to get, to take these averages. So the question for us was always, why do we have these huge fluctuations? Where do they come from? And there again, we think that these these fluctuations in the Metafield actually come from the fluctuations on the Metafield. Like this also starts to become quite clear that the spin projection noise is significant for these dynamics. On the quantitative side, we are not quite at the level that I want to show it, but indeed there's a lot of very interesting stuff going on beyond midfield, I think, and then you can always discuss in detail and look in detail how quantum is this, but there is beyond mean field things going, and fluctuations are a non-negligible part. Good. If there's nothing else, then I would like to take the last 10 minutes that we have to talk about the topic, which actually was slightly different at the beginning and started as from a conference in Bilbao. Actually, in Bilbao there was a talk. I'm not sure anymore who was this, but some talk said we can do beautiful topological experiments in electric circuits. And to be honest, I became very jealous of this. If you build these electric circuits, they cost something like €1,000 if you spend a lot of money. If you build these quantum simulator experiments, they cost €1 million if you don't spend that much money. So the question was actually, is it possible to build local symmetries in electric circuits? Can we do these experiments? It raises also a very interesting question. What is quantum about all these discussions that we are having, and what is classical? A lot of the time you mix these things together, but actually you're having already these local symmetries typically makes the theory so complex that you have a fair amount of engineering and even physical understanding to do to just understand the local symmetries and how do they control the system. So this is a project that we then started, and Hannes was brave enough to look into this, and we wanted really to answer, can we simulate something like local energies and local symmetries in these classical circuits, and what is the possibilities that we have here? Now, we had to start with some Hamiltonian, and what were the basic rules of the Hamiltonian? It has to have a local U1 symmetry. This is what we decided. We want to build a local symmetry. So let's take the Hamiltonian, which is the simplest to implement and has a local U1 symmetry. And if you have such kind of an interaction, you have exactly the local U1 symmetry that you want. So again, the goal is to build a system which is a lattice where we have 5 sides which emulate the Metafield and 4 sides which emulate the gauge field. Yeah. And then they should follow this Hamiltonian here. How do we do this? Well, you can just open your electric engineering book and solve Kirchhoff's rules. And these guys here, these are just harmonic oscillators. So you take a coil and the capacitor, and there is your matter side or your link. Okay, so this is the first ingredient. The second part is not quite as trivial by no means. This is not linear electronics anymore. This is something that is mixing electric fields. So what you have to do is you have to go through Kirchhoff rules, and then you have to take multipliers and connect them in the appropriate fashion such that the system follows the classical equations of motion given by the Hamiltonian. So there's nothing quantum about this whole discussion. We have a classical Hamiltonian, which we solve classically, and we implement this just with classical electronics. And then the question is, how do we do this and how do we verify this again? And then after some time of soldering, this is then the implementation of this Hamiltonian in the lab. So here you have the 5 lattice matter sites. These are coils which you can nicely tune to have the appropriate LC oscillator resonances. These 4 coils are the gauge links. So you have here a system of, you have here a tiny lattice of 5 matter sites and 4 links, and they are connected through these PCB boards, which have the 3 mixers that I have been talking about. And that's then the implementation that you have. And what you can directly implement and measure physically is the voltages on the system. This is what these BNC connectors are for then. And then you can take time traces and spectra and do all the analysis that you typically also do in the quantum world. Okay. So the first thing that we wanted to know is, does the spectrum look right? This Hamiltonian tells us something about the spectrum that it should have. And namely, it tells us that the main frequency of the matter sites should be alternating by this detuning delta. And this is exactly what you can see here. Here you have a positive detuning of 2.5 kilohertz, negative, positive, negative, positive. The second thing that the Hamiltonian tells us is that the gauge field should have to 0th order no energy whatsoever in the rotating frame. This is exactly what we see here. But what you then see also is that these green terms are coupling the bare sides, the 0th order terms, and that you should get some perturbative frequencies or higher order processes. And where should they sit? Well, exactly at an energy of 2 delta positive on this side here. And this is what you can see here. So the coupling is implementing these weak perturbative levels on each side. And due to the Gauss law, you have to mirror this moving also on the gauge fields. So this is also the spectrum. I can put you the perturbation theory over this. It's, they sit where they should sit. Now, you can do a lot of these things, but why do we really typically build dynamic gauge fields and these theories, and why did we come up with them? What we saw is that we can see interactions between particles. Like we have these electrons, and the electrons do not want to sit on each other. They typically repel each other. And then very smart people came up with the idea of the gauge fields in the middle, mediating interactions and so on. Now we have here implemented a system where we have matter sites coupled through gauge fields. So the question is, are we actually implementing interactions here in the system or not in some artificial fashion? So the first thing that we wanted to test is that there is certainly no interaction shift if the gauge field is not dynamical, right? This would be bad if we had this. So we implement the system exactly as we had it, and we just then fix the frequency of the gauge fields and then see what is the spectrum of the matter sites if we drive this first site. So we put particles into the first site and then see what is the frequency of the second site. If there are interactions, you should see a frequency shift. This is what an interaction is in quantum dynamics, right? So with a static link, there's nothing. Now we implement this dynamic. Now we implement the Hamiltonian, as I showed you before, and we want to see how does the system react. And again, what you can see here is we drive the first site, we put particles here, and you have a very nice shift in the frequency, not in the occupation, in the frequency at the point where you have a lot of occupation on the first site. Now we started to look into this, and again, the numerics are looking very nicely. I just, it's not finalized yet, and we're here on YouTube, so I don't want to show things which might have to revise at a later stage. But basically, we can nicely explain again this shift here by some interactions. So we somehow ended up working with gauge fields, and we ended up building a little system where we have suddenly harmonic oscillators who are interacting with each other through this gauge field. And I must admit that this is stimulating a lot of discussions in our group. What are these interactions? How should we understand them? How can we engineer them? How can we use them, and so on in these systems? Given that we have just so directly implemented a full lattice system, which we are working so hard for in the lab for the cold atoms, we have now these kind of systems, the full lattice of 5 sites, and we can just work with it directly. And we have even now here these interaction shifts, which we can implement them. And so this should come out soon, the draft. I will not give any guarantees here, but this is actually a second part which has become very stimulating and fruitful. And so I wanted to show this here to get input, obviously. So this brings me to the end of the second part too. I think I'm 2 or 3 minutes before time, but I hope that's fine. If there are more questions, that's fine too for me. And thank you very much for your attention. I'm open to questions.
Thank you. Let me just check. Okay, so there is a question by Angus Khan. What are some main sources of error? And how long can each simulation last before errors kick in?
Yes. So I assume that he talks about the quantum simulator experiment, and the good thing is the answer is directly shown here on this time evolution graph. So errors typically, I would say we can't look for much longer. If there are no coherent dynamics anymore, then there's no need to go to longer times. So what are these errors? Some errors are just that the magnetic field is not perfectly stable. So if the data slightly changes over time, then the resonance condition will change slightly over time. A second ingredient is that you will have, from experiment to experiment, slightly different atom numbers. I mean, we prepare 300,000 atoms and we do the best we can to have it exactly stable, but the typical atom number fluctuation there is in the order of a few percent, up to 10% actually. Again, you can do so many things about this, but these uncertainties are also non-negligible. Another thing is, for longer and longer waiting times, you will start to lose some atoms. We are under vacuum, but there are still some kind of losses in the system. again, as these atom numbers change, there will be shifts and the dynamics will become off resonance. So changes in atom number and just, you know, instability in the magnetic fields are the main reasons to be worried about on the longer scale. For the lattice system, the main errors will be that we have to cleanly implement the tunneling element, or are actually that we have to cleanly implement the tunneling element, and we only have tunneling which is associated with the spin flips and not with others. There we have to work with energy offsets to really suppress unwanted terms. We are actually, like, again, these fluctuations are increasingly becoming seeming like a very nice tool to look into this. Like you look at the mean field and you look at higher order fluctuations and so on to validate if you actually quantum simulate what you want to simulate, or if you cannot trust this quantum simulator anymore. Yeah, because the Gauss law also gives you very strong restrictions there. But sorry. I hope this answers.
Okay, thank you. I mean, from the written side, I have no more questions. I don't know whether anyone wants to ask any further questions. Yes, sir, you just came in, so do you have any comment, question?
No, thank you.
So I have one. So this is very intriguing. The second part of the talk and this electric circuit. But you know what somehow confuses me is that this is the classical equivalent, right?
Yes.
Of the quantum lattice gauge theory. So, but on the other side, we also know that we can have a kind of circuit QAD or superconducting implementation of a similar circuit for this system. So, so do you think you can, I don't know, push this to the limit, to the quantum limit, or learn something that will help also for the quantum implementations of that?
So this guy here, Landry Breteau, he all he does is superconducting circuits. Okay. So yes, and actually Hannes, he was a master student, and he's now switching over to the superconducting people and working on this. So this is two things. Yes, we think about this, but very specifically, this is a three-wave mixer. This Hamiltonian here in the superconducting world, they call this Josephson ring modulator. If I'm wrong, then I'm sorry for those who are experts. But like this Hamiltonian, Michel Devoré has papers, a lot of papers on this, and this is an element that they use. They just never think about, you know, building lattice gauge theory with this. It's just so exotic for them and esoteric. So I actually think there's a very fair chance to do this. Will I do this in my lab? No. I mean, you can't run efficiently superconducting qubit experiments and atomic mixture experiments. So you know, you have to make a choice there. But I think it's actually a very interesting direction, and we will see who takes this up, and how does the quantum part on these superconducting circuits change all these measurements that we're doing here. I'm very curious to see this. Yeah.
Okay, thank you. Are there any further questions? If not, I would like to thank Fred again for this very, very nice presentation. And I think Rafaela will show something now. Just for the next round of, for the next seminar in our QuantHab series. Okay, so in the next seminar will be by Elias Combarro about exploring applications of quantum computing at CERN. Okay, so that will be on the 8th of September 2021. So I think this is a very exciting aspect that now CERN really fully understands the need to explore this new pathway. Okay, thank you so much to everybody, and see you on our next Contact seminar. And thanks again to Fred for this very nice seminar. Okay.
Yes.
So
thanks everyone for joining in.
See you next time then. Okay.
Thank you.
See you. Bye.